Okay, so those are the three applications. So now we're going to go on to the first one of these. We're going to talk about how to calculate magnetic field vectors produced by a current through a straight wire. So magnetic field vectors produced by current through a straight wire. All right, so say that we have a wire like this, and let's say that the current is going this direction. And say that we want to calculate the magnetic field vectors at 2 points. One is directly above this wire, and let's say that the distance here is 1 centimeter, so 0.01 meters. Say that's point A. And then let's say we want to calculate the magnetic field vector at another point that's farther away. Let's say that that's 0.10 meters away. Okay. So what are the magnetic field vectors at A and B? So in order to calculate a magnetic field vector, we have to know two things: the magnitude and the direction. Okay. We're going to start with, so we need the magnitude and direction. We'll start with the magnitude. That's the easy one. So we're going to use one version of Amperes Law. So it's called Amperes Law. That's Ampere is the guy that the amp is named after. So you can think of this as like version 1. This is the version that applies to straight wires. And the formula says the magnitude of the magnetic field vector, so the value B, is equal to a constant mu sub 0 times the current divided by 2 pi r. I'll tell you what all those values mean. So B is the magnitude of the magnetic field vector. Mu sub 0 is called the permeability of free space. And it is just a statement of how easily magnetic effects can travel through space when there's no magnetic material in between here and there. If there was a magnetic material like iron, you know, if you were trying to calculate the magnetic field vector between an electric current and a point where it was filled with iron in between, iron has a much higher permeability. And so you would have a much higher number here, and for the same amount of current, you'd get a bigger, much bigger magnetic field. And that's why, like, electromagnets are a chunk of iron wrapped with coils of wire, because you get a lot more magnetic effect with that iron core than you would just having those wires wrapped around open space. And this question, this has a value of 4 times pi times 10 to the minus 7th, and then funny units, Tesla meters over amps. And then the last one is R. That is the distance between the current and the desired point. Okay, so let's use these to figure out the magnitude of B at those 2 points A and B. So at the point A, B is equal to 4 pi times 10 to the minus 7. Oh, I didn't give a current for this example. Let's say I is equal to 5 amps. Okay, so at the point A, B is equal to the permeability of free space times the current of 5 amps divided by 2 pi times that R is the distance from the current to the point we're looking at. So if we're looking at this point A, the distance is 0.01. You can cancel some stuff, and the pi's cancel. The 4 divided by 2 just becomes 2. So you have 2 times 10 to the minus 7 times 5 divided by 0.01. And so that is 10 times 10 to the minus 7 times 100. So 10 times 10 to the minus 5. What are the units here? Tesla, right? And that's equal to 1 times 10 to the minus 4 Tesla. And then for the second one, before we plug the numbers in, let's just think about what we expect to happen. Do we expect, so now we're talking about a point that's 10 times farther away. Do we expect that current to produce a bigger or smaller magnetic field? Yeah, it's going to be smaller. If it wasn't smaller, we've talked about this before, there'd be chaos because we'd be thrown around by magnetic fields in different galaxies. And so yeah, as you get farther away, you have to have a smaller effect. And so if you look at that equation, it's going to be, we know it's going to be different by a factor of 10. We know it's going to be, we reasoned that it was going to be smaller by a factor of 10. So we expect this to be 1.0 times 10 to the minus 5th, right? A factor of 10 different. So let's do the calculation. So we get the same cancellations, and we get 2 times 10 to the minus 7 times 5 over 0.1. So that is, up here is 10 times 10 to the minus 7 multiplied by 10. So 10 times 10 to the minus 6 Tesla, and that is 1.0 times 10 to the minus 5th Tesla.
So we might not ever have to do it, but can we plug in any permeability for any material if we're not dealing with free space?
Right, that's right. So if you were doing this, if this was an electromagnet, we'll find out soon that it's much more efficient if you're trying to make a good electromagnet to deal with a coil of wire with a lot of coils. But if you were going to do it with a single wire, yeah, you would want to have it encased in iron, and then you would just look up the permeability of iron. Okay, so now the second step is we have to figure out the direction of those magnetic field vectors. Okay, so the first application of the right-hand rule says point your thumb in the direction of the current. And then your fingers will curl in the direction of the circular field lines which are centered at the wire. Okay, so if you have a current coming out of the page, so use your right hand and point your thumb in the direction of the current. Then all of the field lines are going to be circular, centered at the wire, and they're going to point in the direction that your fingers curl. So they're all going to be going counterclockwise in this case. Okay, any questions about that? So your thumb is coming out and your fingers are showing you that it's a counterclockwise rotation, circular around the wire. Why that is? The only answer that I think could be given, let me think about this. I think I've taken too low of physics classes to answer that, is the problem. Why that is, I don't have an answer for that. It's a good question. Quantum mechanics, because of quantum mechanics. Okay, and so this is with the current coming out of the page. What if you had a current going into the page? Then it's harder on your wrist, but then you point your thumb into the page, your fingers curl this way, and so it's a clockwise set of circles. Okay. So now it's a little hard to visualize with the example that I gave. So in this one, our thumb is going this way, right? So the circles are going, you know, out the top, down the front, in the bottom, up the back, around like that, right? And so the magnetic field vectors, remember, are tangent to these field lines at every point. So on this one, at this point, the magnetic field vector would point this way. Here it would point this way. Here it would point this way. Here it would point this way, right? So for our example, this point that's directly above the wire, what direction is a vector that's tangent to the field line? Yep, it's coming exactly out at us. Can you picture that? So that's the kind of thinking, three-dimensional thinking you're going to have to do these problems. So the circle is going this way. When it's right at the top, a tangent is pointing straight out of the page. And so for part A, if your thumb is going this way, then the field lines are, you can think of them as like a circular path that is out at the top and in at the bottom, okay? So the magnetic field vector at the point A is 1.0 times 10 to the minus fourth Tesla out of the page. You could define a coordinate system and write it as a vector, but I don't expect you to do that. It's sort of unnecessary. It's just, what?
Would it be a positive C then?
It depends how your coordinate system was defined. Getting into three-dimensional coordinate systems, all of a sudden, like you have a lot more choices to make. I think let's just not even worry about it, and let's just give it a magnitude and a direction, and that's a vector. Yep. That's right. Yep.
So you just want to see us show you that it's coming out at us and going in?
You can just say this, or you can draw a picture saying, like another way to say this would be 1.0 times 10 to the minus fourth Tesla, and a little figure there that shows that it's coming out.
So if it was right in front of the wire, then it would be going down.
If it was like just closer to us than the wire, then yes, it would be going down. That's right. And now part B. Now we have a point that's directly below the wire. What's the direction of the magnetic field vector for that? In, yep, and this same figure tells you why. So if you're directly below, the vectors are going straight into the page there. So the magnetic field vector at B is equal to 1.0 times 10 to the minus fifth Tesla into the page or probably a better way to write it is 1.0 times 10 to the minus 5th Tesla, like that. Okay, here's an example I'd like you to work on. So let's say that the current is going into the page, and let's say that it has a magnitude of 20 amps. And let's say that the point where we want to know the magnetic field vector is at a distance of 0.2 meters. What's the magnetic field vector at the point A?